Alright, so let's talk about the heat conductivity tensor. So Q, as we said, Qi is the vector, this is minus Kij u comma j, and in the vector notation this would be Q is minus K gradient of u. So K in general is a tensor, and that's the conductivity matrix or tensor. This is a property of the material and it has to be determined experimentally. Okay? Now you will notice that in principle K can depend on the temperature also. So you can have a material which, when it becomes hotter or colder, its conductivity also changes. Okay? And that would make this law a little bit nonlinear, because then I would have a heat flux that depends on the temperature not only because of the gradient but also these coefficients. So for linear heat conduction, we will have to assume that K does not depend on the temperature field. Okay? K is kind of a temperature independent quantity. We are also going to look at some other aspects. So what about a homogeneous material? So if my property does not depend on the location at which I am, it's same throughout, that's what a homogeneous material would be, and that would imply that K is not a function of x. Okay? So it is constant everywhere. I could have a composite material where K could be different in all directions. So I could have a situation where the conductivity may be of, so I can think of a material like this. So maybe this is wood, and then I have these plates of iron or steel. And then if I look at the conductivity, so perhaps this material has a good conductivity along the x direction, but it has poor conductivity along the y direction. So in general, a material can have conduction which is different in different directions. We are going to talk about an isotropic material where conductivity is same in all directions. And it can be shown that if conductivity is isotropic, then Kij must have a structure something like a constant K times delta Ij. So Kij has a structure of a diagonal matrix, okay? And I have the off diagonal terms which are 0. So the simplest material would be a material which is isotropic as well as homogeneous. So it neither is directional dependent nor it is spatially dependent. You can have combinations of these. So I can have a material which is not isotropic but it is homogeneous, and vice versa. Okay, we are going to talk about very simple cases, and let me write down the strong form of the problem for you. So given some constants f, so this is the heat source which is defined on this domain omega, and the heat source is a real valued function. I will define G as the boundary condition, the Dirichlet boundary condition, it is defined on the domain gamma g, which is the boundary of omega. This is also a real valued function. And I will talk about h, which is defined on gamma h, and this is also a real valued function. So, given these functions, I would like to find a u on omega, which is again a real valued field, such that I will have to now specify my differential equation and the boundary conditions. So, the differential equation is qi comma I equal to f on omega, and u is equal to g on gamma g, and minus qi ni is equal to h on gamma h. This is the strong form of the problem. If you compare it to the one dimensional problem, we had u comma xx equal to f, or u comma xx plus f equal to 0 was our original differential equation, and then we had two boundary conditions, a Dirichlet boundary condition and a Neumann condition. So, very similar. Let me also, to help you, write down the vector counterparts of these equations. So, you will notice qi is a vector, and when I take this comma I, that means it is a divergence. So, we are really talking about that the divergence of the flux q is 0 on omega. So, that is the boundary condition, that is the differential equation, and it is known as the heat equation. So, it will be nice if you can see the relation between the two representations of the heat equation. Both of them are the same equation. This is in the vector form and this is in the simplified index notation, which will help us do certain manipulations. This, of course, is the boundary condition, u equal to g on gamma g, no change on that. This one is a condition on heat flux. So, now the flux is a vector, and I can specify a normal component of this vector. So, in the vector notation, this would imply we are talking about minus q, and the normal to the boundary, this is specified as h on gamma h. Okay? So, I have now shown you the strong form of the problem. You will very well notice that q is related to the temperature field through the Fourier's law, and it already has a derivative in it. So, this equation would actually, I am sorry, this is not 0, this is f. So, this equation is almost like the Poisson's equation, because it would give us something like Laplacian for a certain k. I will talk about that in a minute. And then, of course, the two boundary conditions. If I want to use a method like finite difference method, then I will start from the strong form of the problem and try to approximate so that I can make a mesh and write down the approximate difference equations for the differential equation, and then apply these boundary conditions and ultimately get a system of algebraic equations. On the other hand, if I want to do a Galerkin method, I would have to come up with a weak form for this strong form. Alright, so as we have said, this is the generalized Poisson's equation. Let us define the solution space, because we want to write down the weak form. So, the solution space we will denote by S, and this consists of functions u such that u belong to h1. We have already seen what the meaning of this h1 is. That means the function itself as well as the first derivative they are square integrable. We will also require these functions to satisfy the essential boundary condition, and we are going to take these as the essential boundary condition. So u would be g on gamma g. This is the solution space. And then I am going to specify the weight function space. This will be denoted by the space V. It consists of all functions w, which are h1 again, and they now satisfy the homogeneous Dirichlet boundary condition. So w's are 0 on gamma g. Okay. Let me recall for you that these spaces are for a certain weak form that we have in mind. Okay. Weak form for a given strong form is not unique. Given a strong form, I can propose different kinds of weak forms, as we saw in the example of the one-dimensional equation. We tried integrating by parts once. We also tried a weak form where we do not integrate by parts, and the spaces were different for those two forms. The way I have defined the spaces h1, you can probably already guess that I am going to integrate by parts, and that's why there is only one requirement of one derivative on u, and likewise for w. With this, let us propose the weak form. So I will write it down here. So given f, just as before, a real valued function, g again defined on gamma g, a real valued function, h defined on gamma h, a real valued function, I must find my u that belongs to the solution space S such that I must satisfy for all w's that belong to V the following statement, and it's an integral form. So this I will give it to you and then show it to be true. So w comma I qi times d omega, this is integral over omega w times f d omega plus gamma h wh d gamma. This is the weak form of the problem. Okay? And as I said, it's not unique. For a given strong form, it is possible to get different weak forms, but this possibly is the optimal weak form because it balances the derivatives on w and q or w and u, and therefore the functional requirements, the function space requirements on the weight function and unknowns are balanced, which will help us in coming up with an optimal space for the Galerkin form. We will again go through the proof for showing that S and W are equivalent. So this is what we will set out to, that strong form and the weak form are equivalent. Okay? So you can solve any one of these problems and they are guaranteed to give you exactly the same solution. So the proof. First we will assume that the strong form is satisfied. So U satisfies the strong form, and we will show that it indeed satisfies the weak form also. So assume U is a solution to the strong form. So now what we are saying that this implies that U already belongs to the solution space, and we will choose a W that belongs to V and do the following. W times qi comma I minus f d omega is 0. Okay. So because we satisfy the strong form, so this equation is satisfied strongly at every point in the domain. So I simply take this equation, multiply it with a w which comes from the variation space, and the integral of that is 0. The rest is mechanical. I am going to now integrate this by parts. So if I do that, the first integral would become minus w comma I qi, and I would apply the divergence theorem. So this is omega, the domain. The second term, by applying the divergence theorem, I would get an integral on gamma, and this would be simply w times qi times d omega. Okay? And then of course wf d omega equal to 0. Gamma I know is of two parts. So gamma consists of gamma g and gamma h. So I am going to split the integral. So if I want to write the integral over gamma, I will split it into two parts over gamma g and a gamma h. The integrand remains the same. Okay, so I will do exactly that. So let me talk about this integral. It has two parts, one on gamma g and the other on gamma h. Now please notice the function spaces. On gamma g, w is 0. So when I calculate this integral on gamma g, the integral vanishes because w is 0 on gamma g. Okay, so I don't have to worry about that term. I am only left with the integral on gamma h. However, because I satisfy the Dirichlet boundary condition, so I am going to use this condition that qi ni is h on gamma h. All right, so this therefore I can write, so this integral at the bottom I can write this as minus w comma I qi d omega minus integral over gamma h, and now it becomes w times h d gamma minus integral over omega w times f d omega. And in fact this is what the weak form is. So we have been able to show that this equal to 0 implies that my solution satisfies the weak form. So part A of the proof is done. Now we go to part B, wherein we want to show that, assume that U is a solution to the weak form. And now we would like to derive from it the strong form. To show the strong form, we have to prove two things. Okay? So we have to show that the strong form has the differential equation and the two boundary conditions. Okay? Now you will agree with me that because my solution satisfies the weak form, so this is given to me. Okay? Which means I know U already belongs to the space S. If U belongs to the space S, so this boundary condition is taken care of. So this is done. So therefore if I start from this weak form, I need to show two things. A, this differential equation, and B, this Neumann boundary condition. and again we recall the nomenclature, this is the essential boundary condition, this is the natural boundary condition. So therefore our effort is to start from the weak form and derive the differential equation and the natural boundary condition. So I will write here that since u belongs to S, so u equal to g on gamma g, the essential boundary condition is already satisfied. Now I will take the weak form and integrate by parts again. So I will take the weak form and w comma I qi d omega plus integral over gamma h w times h d gamma plus integral over omega w times h d omega. This is my weak form. I am going to integrate this by parts once again, and therefore so integrate by parts. And this would lead to the following. So I would get a term w times minus qi comma I plus f. So I am just rearranging these terms d omega, and the second term that I get on integration by parts, I am going to club this with the h term, and that would be ni qi plus h d gamma. Okay. What I now need to show is that this term goes to 0 at each and every point in the domain, and this term goes to 0 on gamma h, and independently. Right now they are combined together. So my task is to show this as well as this. This statement is satisfied for all w's that belong to V. So what I am going to do now is, because this is true for a large number of w's, actually infinite of them, so if I can show that even one of those statements, if it implies what I require, then I am done with the proof, because all these statements are satisfied concurrently for all w's. So I am going to be doing the proof in a very clever way. I will choose a w that actually makes this term go to 0, and this term actually vanishes automatically. That is the kind of w I will choose, and that is how we did the one-dimensional problem. So this proof will just be a mirror of that.